Question 19 begins just with a request to write down the expression for Ka for ethanoic acid. So that's the ionisation of ethanoic acid, and Ka, remember, is just the equilibrium constant. It's just the Kc, but specifically for that reaction. So with ionisation in the forward direction, so these go on the top, CH3, COO minus, and H plus, and the unionised form goes on the bottom. So that's the expression. And then it wants us to find the pKa from the idea of the pH. So pH is 2.41, it tells us, and always if you're going to calculate anything from that, the first job is going to be to convert that into H+. So you hopefully remember how to do these things. If you have pH, you have to take 10 to the minus that value to get the original H+ back. So H+ is 10 to the minus pH, which is 10 to the minus 2.41. And on your calculator, that's the inverse of the log function. So you just do shift log of minus 2.41, and you get 0.00389 moles per dm cubed. So that's the first thing. And then we've got to use that to get the Ka value. So the problem with that expression is that it's too complicated. There are too many things we don't know. So whenever you have just the weak acid on its own in solution, as opposed to a buffer solution where it's mixed with added conjugate base, if it's just the weak acid, the approximation you use is that these two concentrations on the top should then be virtually the same. So we can write that Ka is approximately equal to H+ squared divided by the unionised acid. So if we make another approximation, which is that the unionised acid concentration is more or less the same as the total acid concentration because such a small amount is ionised, then we have all the numbers we need, because we've worked out H+ is 0.003890, so that's got to be squared, and the bottom line is just the overall acid concentration, which it tells us in the question is 0.870 moles per dm cubed. So we've just got to compute that to get the value of Ka. So 0.00389 squared divided by 0.87 equals that's 1.739 times 10 to the minus 5 moles per dm cubed. But it wants not just Ka but pKa. So pKa is minus log to the base 10 of Ka. So we just take log of that number. So log of the answer equals 4.76 is the answer to that. Okay, so the pKa is 4.76. Now for part 3, the percentage dissociation is just to work out what the concentration of H+ is, which we know, divided by the total concentration of the acid, because each time it dissociates you get an H+, so the percentage dissociation is the concentration of that divided by the total concentration, and then times 100 to turn it into a percentage. So that's all it means by percentage dissociation. So that's just equal to 0.00389 is the H+ concentration, divided by 0.870, which was the total concentration, times 100. Okay, so we can just work that one out. 0.00389 divided by 0.87, and that's 0.447%. So very low percentage. which is what you expect, because that's the point, it's a weak acid, and we've been working all these calculations based on the assumption that very little ionizes. That's why we can get away with assuming that the total acid concentration is virtually the same as the unionized concentration, so 0.447%. Part B then, again what we have to start with is the pH, which we can then turn into H plus concentration and hence deduce the OH minus concentration and so on. So again you see that the pattern, that as soon as you see a pH, the first thing to do is to turn it into the H plus concentration, which is 10 to the minus pH. So again we can just do that. So we've got inverse log of minus 13.48, which is 3.311 times 10 to the minus 14 moles per dm cubed. So that's the H plus concentration, but obviously this is a question about sodium hydroxide, so we need to relate that to the OH minus concentration, and the key to that is Kw. So you have to learn what Kw is, which is that, okay, the ionic product of water, but you have to think of using it whenever you have a calculation involving alkali, or indeed if it was about the pH of water, then Kw is the key. And what you need to do is just to rearrange that to solve for the one you don't know, which in this case is OH minus. So we get OH minus is equal to Kw divided by H plus. And we know both those numbers because Kw is on your data sheet, is 1.00 times 10 to the minus 14, divided by H plus, which we've just worked out, 3.311 times 10 to the minus 14. Okay, and if we do that sum, we can get the answer. So we divide by 1 times 10 to the minus 14 equals, okay, and that equals 0.3020 moles per dm cubed NaOH, or OH minus at least, is what we've actually calculated. But remember that sodium hydroxide is a strong base, it's completely ionized, so if that's the concentration of OH minus, that's also the concentration of NaOH, because each mole of NaOH provides a mole of OH minus. So we know the concentration of NaOH, and we can turn that into moles, because if we know the moles, we can find the mass and therefore get the percentage mass. Okay, so the next job is to get the moles of NaOH, which is concentration times volume in dm cubed. So that's the concentration, 0.3020, and we're talking about 100 cm cubed, so that's 0.1 dm cubed, which is 0.03020 moles. And we can turn that into a mass. Okay, so mass of NaOH is moles times mR, which is 0.03020 times 40.0 for sodium hydroxide, which is 12.08. Yeah, that's not right. .208, sorry, that looks more like it. 1.208 grams. Okay, which now, as we realised, must be smaller than 1.2x. That's why I realised I'd made a mistake before. So we can just turn that into a percentage. Okay, so the percentage mass, you quite often get problems on that, and you just have to remember that that's equal to the mass of the compound you're interested in, divided by the total mass, and then times 100 to turn it into a percentage. Okay, so it's the actual mass of sodium hydroxide divided by the mass of cleaner times 100. So that's equal to 1.208 divided by 1.26, times 100, which equals 95.9%. Is what you should get for that one. 3 significant figures. Okay, part C wants a dot and cross diagram for a carbonate ion, but they've made it quite easy because they've given you the displayed formula, and so that more or less gives you the answer. So you've got carbon in the middle, 3 oxygens around it, and on this corner we've got a double bond, so we know that's going to be 2 shared pairs. So dot and across, and if we're making the oxygens crosses, that's used 2 out of oxygen 6, so it will have 2 crosses, 2 lone pairs as well, and that's dealt with that oxygen. Now the other 2 are O-. Now that means that they each have their own 6 electrons in the outer shell, plus 1 other one to give it the negative charge. And there's just a single bond, so there's just a single shared pair, there and there, and there and there. So we can now put on the other 5 electrons of the oxygen, because it had 6 altogether. 1, 2, 3, 4, 5. Okay, so that's accounted for the oxygen 6 plus the one it's sharing, but as we just said, it has 1 extra electron as well because it's O-, so you can use any other symbol you like. So let's use a triangle just to be boring, but you could use something more inventive if you wanted. That's the extra electron which gives rise to the O-, and this one's going to be exactly the same, so it's got 1 of its 6 there, so 5 more crosses, 1, 2, 3, 4, 5, and O-, so it has the extra electron as well. And remember, as always, when you have an ion like that, the charge has to go outside the bracket because it's effectively shared out between those atoms. So you just do it like that, and that's all you need.